Good day everyone. Today we are going to start part 2 of electrochemistry, and in this video we are going to complete electrochemical series and Nernst equation. First let's start with electrochemical series. So electrochemical series is the arrangement of various standard half cells in order of their decreasing values of standard reduction potentials. So it is arrangement of the standard reduction potentials of various half cells. It can be negative or positive. Negative E0 means that the redox couple is stronger reducing agent, while positive E0 means that the redox couple is a weaker reducing agent. So let us discuss the applications. First is the stability of the reduced form. So if the standard electrode potential of an electrode is greater than 0, then its reduced form is more stable as compared to hydrogen. Similarly, if the standard electrode potential is less than 0, that is negative value, the hydrogen gas is more stable than the reduced form of the species. Next is the nature of electrode. The electrode with higher electrode potential acts as a cathode, whereas electrode with lower electrode potential will act as anode. Reducing power of species, that is, standard reduction potential of the half cells are arranged from positive to negative. So more negative the EMF value, stronger is the reducing agent. More positive is the EMF value, the weaker is the reducing agent in comparison to hydrogen gas. So in our electrochemical series, Fe will be at the top and lithium plus will be at the bottom. And it also helps in predicting the redox reactions. So electrochemical series also helps to predict the feasibility of redox reaction, thermal stability of metal oxides, and spontaneity of an electrochemical cell by choosing the half cells with appropriate E0 values. So any cell reaction with negative calculated value of EMF will not proceed. Next, we'll study about the uses of electrochemical cells. So they are used for determining the pH of solutions, solubility product and equilibrium constant, and other thermodynamic properties, and for potentiometric values. Now we'll study what is Nernst equation. So this is the equation which gives the relation between electrode potential, heat supplied, and concentration of metal ions. So it is an equation which gives the relation between all the three factors. So first we will study about the Nernst equation for an electrode potential. So the standard potentials are always measured under standard conditions, that is 1 atm of pressure, 1 molar of concentration, and 298 Kelvin. So let us first take this reaction, that is Mn plus n electrons will give rise to M, some metal. So the electrode potential measured against this can be written as this. So this is very important to remember that this is the equation called the Nernst equation. And for pure solids, this M is equal to 1. So the equation will become like this, that is E0 minus RT by NF ln 1 minus n plus 1. Here R is the universal gas constant, which is 8.314 joule kilo per kilomole, and F is the Faraday constant, whose approximate value is 96,500. So here next the ln using logarithms will be converted into log, that is 2.303 will be multiplied. So the reaction will become as follows. And if we take 298 Kelvin and place the values of R and F, we will get the reaction to be as follows, which is E0 minus 0.059 by N log 1 by m to the power n plus 1. Next we'll study the Nernst equation for EMF of a cell. We have completed the electrode potential for Nernst equation. Now Nernst equation for EMF of the cell. Let us take the Daniell cell. We know Daniell cell will have copper and zinc. These are the two respective equations and 2 electrons are involved, and therefore in the place of n we take 2. For finding the cell potential, we'll subtract the anode from cathode. So we'll write the equations and take the ones which are common, and finally we'll get the equation to be E0 minus RT by 2F ln Zn2 plus by Cu2 plus. These are the concentrations of the ions. Now taking 298 Kelvin and R and F values, we get the final equation to be E0 cell minus 0.059 by 2 log Zn2 plus by Cu2 plus. Here we can understand that E cell is directly dependent upon the concentration of Cu2 plus and inversely dependent upon the concentration of Zn2 plus, and E cell decreases as the temperature decreases and the number of electrons involved in the reaction will increase. So let us take the general electrochemical reaction of this type, and the small letters are actually the stoichiometric coefficients. Then here we can write ln and this can be later written in this form, where on top we'll write the products and down we'll write the reactants, and they are raised to the stoichiometric coefficients. So if we take 298 Kelvin and we substitute the R and F values, we get the reaction to be as follows. Now let us solve the question. So we are asked to calculate the EMF of the following cell at 25 degrees Celsius, and this is the cell representation, where E0 of Fe is given and E0 of H2 is also given. So from this representation we can understand the reaction to be Fe plus 2H plus will get raised to Fe2 plus H2. So here we will subtract the anode from cathode and we get the E0 cell to be 0.44 volt. And the E cell can be calculated using the Nernst equation, and we are already given with these concentrations in the cell representation. So finally we get the answer to be 0.41 volt. Now let us study the equilibrium constant from a Nernst equation. How do we actually get the equilibrium constant from a Nernst equation? So let us take the Daniell cell, and this is the equation which we know. Zn plus Cu2 plus will give rise to Zn2 plus Cu, and the concentration of Zn2 plus keeps on increasing and the concentration of Cu2 plus keeps on decreasing with time. At the same time, the voltage of the cell on the voltmeter keeps on reducing. So after some time, there will be no change in the concentration of Zn2 plus and Cu2 plus ions, and at the same time the voltmeter will give 0 reading. So you can understand that at equilibrium the E0 cell is equal to 0, and so our Nernst equation can be equated to this, and when we bring the E0 cell this side, we get the equation to be as follows. That is, E0 cell is equal to 2.303 RT by 2F log Zn2 plus by Cu2 plus. So at equilibrium we can say that Zn2 plus by Cu2 plus is equal to constant, which is Kc. And at 298 Kelvin we can actually write the equation to be E0 cell is equal to 0.059 by 2 log Kc, which can be equated to 1.1 volt, which we know is the EMF for a Daniell cell. So keeping this value this side and substituting all the other values, we get the answer of Kc to be 2 into 10 to the power 37. And since such a high value of Kc is obtained, it shows that the reaction has proceeded almost to the completion before attainment of the equilibrium condition. And hence, the value of Kc will help us identify the extent of cell reaction. Let us solve a question. Here we are asked to calculate the equilibrium constant for the reaction. Fe plus Cd2 plus will give rise to Fe2 plus Cd. So here E0 value is given for Cd2 plus and for Fe2 plus. So we know that E0 of cathode minus E0 of anode. So we'll substitute these values and we'll get the E0 of cell to be 0.04 volt. and then we'll place this in the Nernst equation and get the final value of Kc to be 22.70. Now we'll study what is the concentration cells. So two electrodes of the same metal are placed separately in two solutions with same electrolyte having different concentrations, and these two are connected with a salt bridge. So this is called the concentration cells. Example is copper ion concentration cell. So the equation can be written, cell representation can be in this form, and this is the salt bridge, and Cu2 plus slash Cu. Here it is Cu slash Cu2 plus salt bridge, Cu2 plus slash Cu. So here the electrode placed in high concentration acts as a cathode, and placed in low concentration will act as anode. So this is the whole construction of concentration cells. Now we'll study about the electrochemical cells and Gibbs energy of the reaction. So when a cell reaction will take place, the electrical energy is produced, which can quantitatively be converted into work. So the electric work done by the cell results in corresponding decrease in the free energy of the cell. So the electric work which is done in 1 second is multiplied, is the product of EMF into the charge which is passed. So to obtain the maximum work from the galvanic cell, the charge has to be passed reversibly. So the reversible work done by the galvanic cell is equal to the decrease in the Gibbs energy. So we can write this equation by the statement. That is, work done is equal to negative of delta G. We know the delta G formula to be minus NFE cell. For standard conditions, we can write E naught cell. So then, by placing the value of E naught, we can get the delta G naught is equal to minus 2.303 RT log Kc. Here E cell is an intrinsic property, while delta G is an extensive property because it depends on the value of N. So now, at the stage of chemical equilibrium of a cell, the E cell is equal to 0. Subsequently, the delta G will also be equal because the formula is like this. So if the E cell is 0, then delta G will also be 0. So this reaction is only possible if E cell is positive and delta G is negative. So this is the chemical equilibrium. Now let us solve the question. The standard electrode potential for Daniell cell is given. So you have to calculate the delta G for this reaction, and the reaction is given. So simply by placing these values, we can get the answer to be delta G naught is equal to minus 212,300 joule per mole. So we have completed the detailed explanation of electrochemical series and also the Nernst equation. So in the next video, we will be completing the conductivity of electrolytic solutions and its measurements, and we'll study the ncert for both the parts at the same time. Thank you so much for watching. Stay tuned for more parts.